Hello, my name is Aditya, and I'm going to be talking to you about active automaton inference for reinforcement learning using queries and counterexamples. Hopefully, by the end of the presentation, you can see what our work proposes and how it fits in the domain of explainable AI. Let's get started. In recent years, deep reinforcement learning has achieved human-level performance in a variety of tasks. For example, AlphaGo is a program that can play the game of Go better than the world's best human player. However, these systems come with their own problems. For one, the data exploration required takes an extensive amount of time, making these systems harder to train. And second, it's often hard to interpret how these systems are making decisions. Towards solving both of these problems, we propose a system that infers a finite reward automaton. Here's an example of one. Our system, the method that we propose, is faster and more interpretable than baseline methods. I'm going to proceed in explaining our idea by first discussing the interpretability of finite reward automata, then detailing our algorithm, and concluding with our experimental results. Let's start with interpretability. Say you have a robot that's in an office. You want this robot to get you coffee and then get you files in that order. In order to incentivize the robot to do this, you create a non-Markovian reward function. The function gives a reward of 1 if the robot gets both coffee and then files, and gives a reward of 0 otherwise. We use a Markov decision process to describe the overall environment of the robot, that is your office, and how the robot can move through the office. And we use the non-Markovian reward function, again, to incentivize it to get you coffee and then files in that order. Now let's talk about an example of finite reward automata. Here's an example down here. As you can see, this automata has many states and transitions between those states. The agent starts off in state 0. If the agent gets coffee, it moves to the next state. If it doesn't get coffee, it stays in this state. In both cases, it gets a reward of 0. In state 1, if the agent gets files, it moves to the last state and gets a reward of 1. And if it doesn't get files, it stays in the same state and gets a reward of 0. Now, what you will notice about both this reward automaton and the non-Markovian reward function is that they will give the same reward for the same actions. If you get coffee and then files, both of them will give you a reward of 1. And if you get files but not coffee, or get files and then coffee, both of them will give you a reward of 0. This scenario shows that an FRA can encode a non-Markovian reward function. This is important for reinforcement learning. In our system, the agent does not know what the task is and therefore doesn't even know what the reward function is. Our system works by having the agent infer a FRA that can encode the non-Markovian reward function of the MDP. Now, what makes this FRA interpretable, you may ask? Well, say that this is what the agent believes the FRA that encodes the non-Markovian reward function is. This is what it believes, its hypothesis. What you can say, how you can interpret this, is that the agent thinks it needs to get coffee and then files in that order. Because if the agent gets coffee and then files, it moves from state 0 to the final state, and it gets a reward of 1. In other words, an FRA allows you to see what the agent is thinking its objective is. Another question you may have is whether or not this FRA can be used in a variety of scenarios. After all, is it always possible that an FRA can encode a non-Markovian reward function? The answer is yes. And we show that for non-Markovian reward functions that are finite value, there will always exist at least one FRA that can encode that function. And therefore, our method is applicable in many scenarios. So in conclusion, we've detailed how FRAs allow you to see what the machine is thinking and also can be applied to a variety of scenarios. Now let's move on to our algorithm. The goal of our algorithm is to get an optimal policy for the RL scenario. We do this by having the sub-goal of inferring a finite reward automaton that encodes the MDP's non-Markovian reward function. Our approach is based on L-star learning, a method developed in the 1980s. It consists of a teacher and a student. The teacher's job is to answer questions from the student, and the student's job is to learn a certain process. In our algorithm, the teacher's role is fulfilled by our reinforcement learning engines, and the inference engine is our student. The first question an inference engine can ask is a membership query. That is, do these actions get me a certain reward? After enough membership queries are asked and answered, the inference engine can create a hypothesis FRA. Now it can ask an equivalence query. That is this FRA correct? Both of these questions are yes/no questions and are answered by the teacher. Now let's get a more granular view. Here is our approach. In the center, you can find the inference engine, and the RL engine and active RL engine represent our teachers. Let's detail how the process works. You start off with a random policy that's sent to the inference engine. Initially, the inference engine doesn't have any information to construct a hypothesis FRA. So it asks a series of membership queries. The active RL engine will explore the environment and answer these queries. Now that the inference engine has enough information, it's going to generate a hypothesis FRA. Now it's going to ask an equivalence query. The regular RL engine will perform reinforcement learning, specifically Q learning, until it finds a counterexample. Here's an example of a counterexample. Say that during reinforcement learning, we find that when the agent gets coffee and then files, it gets a reward of 0. Now that's not what our FRA says. It says that we should get a reward of 1. And this means that our FRA is incorrect. In order to help the inference engine correct its hypothesis, this trace, coffee, files, reward of 0, is called a counterexample, and it's sent back to the inference engine to help it refine its hypothesis. If no counterexamples are found, then we're in this yes branch, and we continue to perform Q learning until we find convergence. Let's move on to the results. For our case studies, we used the office world environment. This consists of an agent noted by the triangle, and the agent's job is to get a series of objects. A represents coffee, B represents files, and C represents a pen. We have a variety of tasks here. Let's explain what they mean. ABAC would mean get coffee, then files, then coffee, and then get a pen. As you see, the later tasks are not only longer, but more complicated. Now let's see what algorithms we're going to compare it against. We have 3 algorithms that we compare it against, 2 of which use finite reward automata, and the last of which is a deep reinforcement learning algorithm. Finally, for the graphs I'm about to show you, this shows the attained rewards from 10 independent simulation runs, where the reward represented is averaged every 10 training steps. Now let's go into the graphs. In the first task, we can see that our algorithm converges because we see a horizontal green line and no shadow underneath. Meanwhile, the other algorithms do not converge. Similarly, with task 2, our algorithm converges while the other algorithms do not. And finally, in task 3, the bottom 2 algorithms do not, while the top 2 algorithms do converge. However, our algorithm will converges around 500,000 training steps earlier. In conclusion, in this abstract, we propose a new method that does reinforcement learning by actively inferring FRAs. We show that this method is faster in our results and more interpretable because it uses FRAs. Finally, we show that FRAs can be used in any scenario where we have non-Markovian reward functions. For future works, we can look to scenarios where the teacher incorrectly answers membership queries or where there are multiple agents. Thank you so much for listening, and I hope you enjoyed our presentation.